Hi everyone, today we are going to talk about the Zynq architecture by Xilinx. So the objectives are that at the end of this video you will be able to identify the basic building blocks of the Zynq architecture processing system, also known as PS. You will be able to describe the ARM Cortex A9 processor memory space. You will be able to connect the processing system to the programmable logic, also known as PL, through the XI ports. You'll be able to generate clocking sources for the programmable logic peripherals. You'll be able to name the 5 XI channels, and you will be able to describe the operations of the XI streaming protocol. So let's get started. If you are new here, make sure you subscribe and click the like button as well. Right. So the outline of this video is about the Zynq system on chip. SoC means system on chip. The Zynq system on chip processing system, the processor peripherals, clock, reset and debug features, the XI interface, and lastly the summary. So this is the outline of the video. So we are going to start with the processing system and the programmable logic. So for the processing system of a Zynq architecture comprises of ARM Cortex A9 processors, memory interfaces, peripherals, which may be a USB cable or Ethernet, and a dedicated interconnect for communication. So the processing system of a Zynq system on chip architecture has ARM Cortex A9, memory interfaces, and peripherals. So this is the basic structure of an Zynq 7000 system on chip architecture. It consists mainly of two major sections. The first section is the processor and the second section is the programmable logic. Right? The processor consists of peripherals, ARM Cortex, and memory interfaces. The second section of the processing system, the second section of the Zynq 7000 system on chip is the programmable logic. The programmable logic is a reconfigurable FPGA fabric that allows custom hardware implementation. This means that this programmable logic can be programmed using languages like VHDL, or Verilog to allow custom hardware implementation. So the programmable logic, which is also known as PL, contains a reconfigurable FPGA. So it also shares the same 7 series programmable logic, which are Z7010, Z7015, and Z7020. It also shares with Kintex based devices, which are listed as shown below. So when you say that the programmable logic part of the Zynq 7000 system on chip contains a reconfigurable FPGA, we mean that the FPGA can be reconfigured to allow certain customization of a certain circuit, or to allow customization of a hardware implementation. What do we mean by FPGA? FPGA simply means that field programmable logic array. Field programmable gate array, sorry. Field programmable gate array. What is FPGA? An FPGA is an IC or integrated circuit which is designed to be configured by the user after manufacturing. So an FPGA is simply an IC, but that IC is designed that it can be reprogrammed, it's reconfigurable to allow customization of a circuit implementation. It is far much different from traditional integrated circuits, because the traditional integrated circuits, you have some sort of fixed functions. Say for example, we know the 7400 chip, which may consist of probably NAND gates or AND gates, whatever. They perform that specific function, but the only difference is that an FPGA or field programmable gate array can be reconfigured on a software, right? After reconfiguration, this reconfiguration is important for customizing circuit implementation, which means the FPGA can be programmed to perform addition or subtraction, or to act a certain way which is not fixed. So we are going to move to a section of the processing system, which is the ARM Cortex A9. So what we have covered so far is that the Zynq system on chip, the 7000 series, consists of two sections: the processing system and the programmable logic section. The processing system with the ARM Cortex 9 and the programmable logic section is the FPGA, which shares the same 7 series programmable logic as ATIX or kinetics. So we are now focusing on the processing system. Right. Like I said, the processing system is an ARM Cortex A9 processor. We have a complete ARM based processing system. This complete ARM based processing system is an application processor unit known as APU. We have a dual ARM Cortex A9 processor, caches and support blocks, fully integrated memory controllers, and I/O peripherals. Right? So, which means that the ARM Cortex A9 processor, which is part of the Zynq system on chip or SoC 7000 family, it uses unified memory space. ARM Cortex A9 uses unified memory. What do we mean by unified memory? So we have the key aspects of the memory space, which have or which include the physical memory, which is the RAM, the ROM, and other mapped peripherals. So that's for the RAM and the ROM fall under the physical memory of the ARM Cortex A9. We have address space on the ARM Cortex A9 processor, which is divided into regions for DDR memory, on-chip RAM or OCM, peripherals, and programmable logic. So what we are saying is that an ARM Cortex A9 consists of a physical memory, which is RAM and ROM. It also have address space. The address space is divided into regions, namely the DDR and the OCM. It does caching. It uses L1 and L2 caches to optimize access speed. So the caches and the support blocks are there in the ARM processor to optimize the access speeds. We also have memory mapping, which is under fully integrated memory controllers. This means that the ARM processor can directly access the addresses on the programmable logic or external devices using XI interconnects. Then we have tightly integrated programmable logic. So the tightly integrated programmable logic is used to extend the processing system, is used to have a scalable density and performance. We have a flexible array of I/O which provides a wide range of multi-standard I/O, a high-performance integrated serial transceivers, analog to digital converter inputs. So this is the Zynq 7000 system on chip block diagram. As you can see, so now we move to the processing system components. The processing system components on the processing system, like I said, the Zynq 7000 system on chip family consists of processing system and programmable logic. The processing system is the ARM Cortex A9 and the programmable logic is the FPGA, which means field programmable gate array. Why do we use FPGA? We use FPGA because it can be reconfigured to allow custom implementation on a hardware device. So the processing system consists of APU, it consists of I/O peripherals, which can be multiplexed or extended multiplexed. We have memory interfaces, we have processing system interconnect, we have DMA, we have timers, which may be public or private, we have general interrupt controller, we have on-chip memory, which is RAM, we have a debug controller, which is known as core site. So these are the components of the processing system on a Zynq FPGA, on a Zynq system on chip 7000 family. Right, now we are going to the outline, the second part. The second part is we are talking about the processing system of the system on chip, the Zynq system on chip. So we said that the Zynq system on chip consists of two sections, the programmable logic and the processing system. Now we are now focusing on the processing system. The processing system consists of the ARM Cortex 9, which I am going to focus on mostly. So the ARM Cortex A9 processor implements the ARM v7A architecture. So What does that mean? It means that the ARM v7 is the ARM instruction set architecture called ISA. The ARM v7A is the application set that includes support for memory management unit. So in the ARM processor we need a memory management. So we will have an ARM v7A, which is an application set that includes that memory management unit or MMU. The ARM v7 alone is the ARM ISA or instruction set architecture. Then we have the ARM v7R, which is a real-time set that includes support for a memory protection unit. And then we'll have an ARM v7M, which is a microcontroller. It is a microcontroller set that is the smallest set. So in summary, the ARM Cortex A9 processor implements ARM v7. Understood? It implements ARM v7. And the ARM v7 we have variables. We have the ARM v7, ARM v7A, ARM v7R, ARM v7M. The ARM v7 is the ARM ISA or instruction set architecture. The ARM v7A is the application that includes support for memory management unit. So for the application is for MMU. The ARM v7R is a real-time set that includes MPU or memory protection unit, and the ARM v7M is the microcontroller, which is the smallest set. So we have ARM v7A, ARM v7, ARM v7R, and ARM v7M. The ARM v7 is the ARM ISA. The ARM v7A is the application that manages or that includes MMU. The ARM v7R is the real-time set that includes MPU, and the ARM7M is the microcontroller. So we need to look at what the ARM v7 ISA does. So the ARM v7 ISA includes the following types of instruction. So the ISA, which is the instruction set architecture, has two types of instructions. Why it has two types of instructions? The reason why it has two types of instruction is that we need to have backwards compatibility. So ARM v7, which is the ARM ISA or instruction set architecture, it has two instructions for backward compatibility. Then what are those instructions? We have thumb instructions, we have neon instruction. What does thumb instruction means? The thumb instruction is a 16 bits one thumb instruction, and thumb 2 instructions is a 32 bits instruction. The neon instruction is also known as the single instruction multiple dot instructions, or SIMD instruction. Why do we need 16 bits instructions? The 16 bits instructions aims to reduce the memory usage while maintaining performance. The thumb 2 instructions is a mix of 16-bit and 32-bit instructions, improving flexibility and efficiency of the processing system. But we haven't talked what is an ARM v7. An ARM v7, like the definition here, is an ARM ISA or ARM instruction set architecture. This ARM ISA defines the capabilities and the features of the processor. Then we have an ARM Advanced Microcontroller Bus Architecture, or AMBA protocol. What is this all about? So this one, it defines since it is a protocol, it defines the standards for communication with the ARM architecture. So whenever you hear about communication, we need interface. The communication is done through an interface. So for an interface, we need an XI, or Advanced Extensible Interface. So an XI is known as an Advanced Extensible Interface. This is very important for communication, and it's very important for AMBA, or Advanced Microcontroller Bus Architecture protocol. It's very important for AMBA protocol, right? So we have two types of XI. We have XI13, the XI3, and the XI4. So the Xi3 is a third generation ARM interface. A third generation standard or a third generation ARM interface standard is called an Xi3. It is therefore or is used to support best data transfers for improved speed and efficiency. So the Xi3 is a third generation ARM interface which is used to support the movement of burst data for speed and efficiency purposes. The Xi4 is an enhanced version of Xi3 or advanced extensible interface. So the advanced extensible interface 4 is an extension or is an enhanced version of the advanced extensible interface 3, which is a third generation. Why do we need it? We need it for the support of transfer of large data width, extended burst length, and improved memory mapping. So for the advanced extensible interfaces, we have a third generation and a fourth generation. A third generation is for speed and efficiency and transfer of burst data. The fourth generation, which is the advanced extensible interface 4, is important for improved memory mapping. Then we have a Cortex. A Cortex is a new family of processors. The ARM's Cortex are a newer generation with advanced capabilities as compared to the ARM processors. The Cortex processors include memory management units. For handling virtual memory, enabling modern operating system, which means that the Cortex alone, which is a new family of processors, is different from the old ones. Why? Because itself contains an MMU, while the previous or the old ones, which is the ARM Cortex A9, implements the ARM v7A, which is an application set that includes the MMU or the memory management unit. But the Cortex itself doesn't have to implement the ARM v7A. That's the only difference. And the Cortex, which is a new family of processors, contains MPUs, which is a memory protection unit. It doesn't have to implement the ARM v7R. That's the only difference. So the only difference is the ARM Cortex A9, which is the old generation of chips, and the Cortex is that ARM Cortex A9 has to implement ARM7 architecture, but the Cortex is inbuilt MMUs and MPUs. MMU means the memory management unit, and the MPU is memory protection unit. The memory management unit is done by the ARMv7A in the ARM Cortex A9, and the MPUs are done by the ARMv7R in the ARM Cortex A9. So now we are going to the ARM Cortex A9 processor power. So before we move to the ARM Cortex A9 processor power, we need to summarize the ARM Cortex A9's architecture and how it fits within the ARM v7 family. So the key takeaway is that the flexibility of ARM's architecture, offering solutions for applications ranging from microcontrollers, which is the ARM v7M, to full-fledged operation system, which is ARM v7A. It also highlights the role of AMBA protocols, which are a set of instructions containing two instructions protocols as shown here. The AMBA, or the advanced microcontroller, the AMBA is the advanced microcontroller bus architecture. So it is a bus architecture which contains protocols. The protocols are there for communication, like I said before, and the communication is done through interfaces. The advanced extensible interface 3, which is the third generation, and the advanced extensible interface 4, which is the fourth generation or an advancement of the XI3. So we now need to look at the ARM Cortex A9 processor power. The ARM Cortex A9 processor power is listed here. The ARM Cortex A9 processor power consists of a dual core processor cluster. It consists of a 2.5 GMIP per hertz per processor. It consists of a Harvard architecture. It has a self-contained 32 kilobytes L1 caches for instructions and data. Remember the importance of caching. The ARM based processing system consists of caches for speeding the processing system. That's why we need caches. And I'm going to explain the processor power of the ARM Cortex A9. I'm going to explain each of these. We have an external memory of 512 kilobytes L2 latch, L2 cache. We have automatic cache coherence between processor cores. We have 1 GHz operation, which is the fastest speed grade. So we are going to explain what is a dual core processor cluster. A dual core processor cluster is a dual core architecture. When you hear the word dual, it means two. So this means that the ARM Cortex-A9 consists of two processing cores, and these cores can execute tasks in parallel. So the advantage of having a dual core processor cluster is that we need parallel processing, which will make the processing system faster. So the tasks can be executed in a parallel manner, improving the efficiency and performance for multitasking and complex operations. So we need a dual core processor cluster to processing cores. So a dual core processing cluster means two processing cores which can execute tasks in a parallel manner, allowing high performance and high efficiency for multitasking and solving complex operations or doing complex operations. The 2.5 DMIP per megahertz per processor is a measure of processor performance. What does DMIP per megahertz per processor means? So DMIP is known as Dryston millions instructions per second. DMIP means Dryston million instructions per second. So the ARM Cortex-A9 is 2.5 Dryston million instruction per second. Per megahertz per processor. So each processor is 2.5 Dryston million instructions per second, which is super fast or super efficient. So which means that at 2.5 DMIPs per hertz, the Cortex-A9 provides high computational efficiency for each processor core. So far we've covered two features. We've covered dual core processor cluster and 2.5 DMIP per megahertz per processor. Now we are talking about the Harvard architecture. So when you hear the word Harvard, just think about separate. Harvard separate. That's how you can memorize it. So when you talk about this Harvard architecture, we are saying that the processor uses Harvard architecture, and this means that the instruction and the data memory are separate. We have separate instruction with separate data memory. This allows, of course, for simultaneous access to instructions and data, improving efficiency and performance. Right? This means that when we need to access data, we don't have to wait for instruction to process the first. This can be done simultaneous. That's why we have a Harvard architecture. This so that it can be done simultaneously. So these are the advantages. We first talked about the dual core processor cluster. We secondly talked about the 2.5G MIP per megahertz per processor, and now we are talking about the Harvard architecture. And you said that the dual core processor cluster means that we have two core processors to increase performance and efficiency in multitasking and executing complex issues or complex implementations. And we talked about 2.5 DMIPs or dry stone millions instructions per second per megahertz for each processor, which means that this is super fast computation. And we have the Harvard architecture, and we talked about it is, when you hear about Harvard, think about the separate instruction and data memory, so that we can access data and have instructions simultaneously at the same time. All these are done to increase the efficiency and performance of the processor. Then the fourth one, we have a self-contained 32 kilobytes L1 cache. This is for instruction and data, of course. The 32 kilobyte L1 cache is a very small memory as you can see. 32 kilobytes. I don't remember if there is still an image or a music or video which has got a memory of 32 kilobytes. I don't know if it still exists in real nature. So this self-contained 32 kilobyte is a very small memory and fast, which can be used to increase the efficiency. How can we increase the efficiency with a 32 kilobyte L1 cache? It is for fast access of data and instructions, because this data is frequently used, so we need a fast access. That's why we have a 32 kilobyte L1 cache. Then we have an external memory, of course, of 512 kilobytes cache memory. L2 means level 2, so we have a 32 level 1 cache, which is used for fast access of data instructions, and this is self-contained. The 32 kilobyte one is self-contained. The 512 is an external level 2 cache, which is shared between the cores, because we have two cores, remember, for multitasking and increasing the performance. It has a larger memory than level 1 cache because it is shared between the dual cores. This is large, as you can see. It's 512 as compared to the level 1 cache, which is 32 kilobytes, so as to provide additional storage for the L1 cache. And this storage is needed for data and instructions that don't fit in the level 1 cache. So we have an automatic cache coherence between the processor cores. This is really important. It's really important. What is automatic cache coherence? The Cortex A9 or the ARM Cortex A9 supports automatic cache coherence. This means that it ensures that data in the caches of multiple cores remains consistent. So coherence means consistent. So we need an ACC, or automatic coherence, an automatic cache coherence, for consistency of data instructions in multiple cores. And we have a 1 gigahertz operation. As we know that the processor operates at a clock speed of 1 gigahertz. 1 gigahertz simply means 1 billion cycles per second, which is the fastest speed grade. The high speed allows quick execution of instructions, making it suitable for demanding application. So that is about the ARM Cortex A9 processor. So tune in for the next video where we'll talk about the ARM Cortex A9 processor micro architecture. Thank you very much. If you are new here, don't forget to like the video and subscribe and share. Thank you very much.